to every lecture for in my first year was econ.
There you go. We just need to make this class harder because Jordan wasn't coming. Um, okay, so let's pick off at the end of last week. We did something that had some like factorials in it, right? Because we were differentiating polynomials. I want to start off with something a little bit similar. Okay, and hopefully this shouldn't take too bad because I don't, one, it's very similar to what we had before, but two, if you read the question carefully, an answer should pop out to you very, very quickly. Okay. So again, I really want to emphasize, read the question very, very carefully, right? This is the sort of thing that like, if you're getting into a pattern of, oh, I've seen a question like this before, let me just immediately write down what the answer is, then you could get the wrong answer. So and I am very concerned with what I'm seeing so far. There we go. It took 19 votes for someone to vote the right answer. Okay. So like I said, I don't want to spend too long on this question because they're actually, we did something very similar to it last time. So I'm going to give you about 30 more seconds here. And again, if you have no idea, just throw your answer in. Yeah, exactly. The
I feel
2021.
like breakout rooms might not help this one.
Yeah, I don't think they will. Because as soon as I point it out, people are going to hit themselves in the head. So 10 more seconds. Get your votes in. Even if you don't know, let's just add to the noise. Maybe you'll guess correctly. Okay. Oh, this is beautiful. This is wonderful. I love it. Okay, so it's fairly uniform. The correct answer is A, which of the, how many votes were there? 46 votes. 2 people voted correctly. Yeah. Nice. Okay. So everyone, I want you to read the question very, very carefully. Right. Did you all miss the k bigger than n bit? So let's think about what this is saying, right? Our polynomial is x to the power of n, and we're differentiating it k times, but k is bigger than n. So if we, yeah, exactly. So let's think about this. Like, let's say I give you x cubed, and I asked you to differentiate it 5 times, right? There, n is 3 and k is 5. So if I give you x cubed and told you to differentiate it 5 times, what would you get? Okay, and if you don't know, compute it right now. Just, grind out the 3 or 4 derivatives. It's pretty quick, and you'll see what happens very, very quickly. All right, what do you get? And more importantly, why do you get this? Because it sounds to me as though some of us who guessed 0 might have guessed it, right? Instead of actually knowing it. Right, and Abdul Rahman, why do we get 0? Like what happens? I don't know what you mean by prim, but like maybe derivative? Like the derivative of the constant? Is that what you mean, Jufeng?
I'm assuming he means prime.
Oh, yes, the prime of constant. Yeah. Exactly. So if you have a polynomial like x cubed, when you differentiate it 3 times, you get a constant, right? Because remember, the power decreases by 1 every single time. So if I give you x to the n, when you differentiate it n times, you eventually have a constant. Exactly. You derive more than you can chew. And that's a great way of saying it. Like you just keep deriving so many times that eventually your polynomial becomes a constant. And then by the time you differentiate that, it goes to 0, right? So if you differentiate x to the n more than n times, you will always get 0. So with this question, right, this was kind of the important part right here, this k bigger than n. And if you see that, and hopefully you kind of think about, what happens with polynomials, you just can immediately go to the correct answer being A. All right. So you want to be a little bit careful with that. This is one of those questions that, if this had come up on a test, I think some people maybe just kind of read it too quickly, which is why I was trying to give you the warning to read it a little bit slower and be a little bit more careful. But again, for those of you who, for example, chose C and D, if k is bigger than n, these are negative numbers, right? And what is negative 3 factorial? We don't really know how to make sense of that, right? So, there's also something to be said there, which is just about sanity checking. Now, in a lot of cases, especially with these, one thing I want to point out in terms of problem solving is that if you're not certain, you're like, oh man, there's k's and n's and there's inequalities, and it's kind of difficult to track everything. Choose numbers, right? Choose a k which is bigger than n. Let n be 3 and let k be 5 and see what happens. And then maybe change the numbers a bit and let n be 2 and let k be 7 and see if you can see a pattern. In terms of problem solving, like, if you're writing up your answer, you're not allowed to give examples like that, but you can get an idea of what's happening by actually choosing numbers, right? And you shouldn't be afraid to do that. So there's a little bit of a gotcha. Okay, just be a little bit more careful about that. Now, what I think some of you wanted was this one. So I don't know if you could actually tell here. So I am actually switching the question because the only thing that's changing is the sign here. Okay, so here's the next question, which we won't necessarily do because we did it last time. But now if k is less than or equal to n, so this is the more interesting question because now you're not going to get 0 because you're differentiating fewer times than the degree of your polynomial. And what we found at the end of last time is that this is the answer you're going to get, right? So the answer here is D. All right, and maybe we can go over that very quickly. So for those of you maybe we did it in the office hours last time. Did we actually go over it in the after class? So maybe some people missed it. I'm not certain. Anyone who was here, do you remember? Did we do it afterwards?
I don't think we did the general case.
Okay. There was something there, but I didn't. Yeah. It was the fourth question. Yeah, so we did it, Abdul Rahman, but we did the 2021. I'm not sure that we did the general. Maybe let's just do that really, really quickly here. So we have, where is my functions? We have f equals x to the n, okay? So let's just start. Okay, well, let's do it in general. Let's differentiate once, and we're just going to do it a couple times till we start to see a pattern, right? So we get x or n x to the n minus 1, right? We all know that. That's the power rule, and we're pretty comfortable with that. And if we differentiate again, I'm going to get n. So now I'm going to pull down that n minus 1 and decrease that by 1. I'm going to take 3 derivatives, n minus 1. Now we're going to pull down that n minus 2 and subtract 1. And let's do one more just to kind of see what this looks like. N minus 1, n minus 2, x to the n minus 4, like that.
You're missing n minus 3.
What? Oh, yeah, you're right. I am. Thank you. N minus 3, x to the n minus 4. Okay, great. So anytime that you're asked to do these higher derivative questions, you want to just do a couple of examples and see if you can identify the pattern, right? So All right, this thing right here, that's a little bit weird. We'll kind of come back to that later. What we do notice, though, is that the degree of x to the n, well, it seems that the number of derivatives we take is exactly what we subtract there, right? So that kind of gives us a nice little hint that maybe when I take k derivatives, I'll get something, whatever this n times n minus 1 times n minus 2 stuff is, whatever that is. But it seems like we're going to get x to the n minus k here, right? So that's kind of a good start. And again, we see that kind of consistently, right? We take 3 derivatives, we get n minus 3. We take 2 derivatives, we get n minus 2. Okay, so we kind of start to recognize those patterns. So, okay, so that more or less eliminates C, right? Because that C just is an x to the k. I don't know if you guys remember what the options were, but that throws out C. So now we need to figure out what this thing that I've underlined in the brace is, right? Like, what is this n times n minus 1 times n minus 2 times n minus 3? Now, you've all seen this before, right? When we did combinatorics, that was precisely n pick k, right? So this thing here, for example, right, that was n pick 2. This thing was n pick 3. This thing is n pick 4, right? So we hypothesize this thing is n pick k. Now, n pick k doesn't show up here, right? It's not one of the options. So we have to write out what actually n pick k was. And if you remember its formula, it was n factorial divided by n minus k factorial, right? That's what n pick k was. And that is option number D. Okay, so there you have it. That's how you kind of set it up. You have to do a couple of them. K less than or equal to n, Kevin. K less than or equal to n, right? The number of derivatives that we take, k is the number of times we differentiate. So we want the number of derivatives that we take to be less than the degree, exactly, right? And again, you can always sanity check that just by looking at this number, right? Because if k is bigger than or equal to n, that number could be negative, right? And so we have to be a little bit careful about that. But yeah, less like inequalities, right? Yes, Stephanie, absolutely, you are allowed to do this sort of thing. And in part, the reason for that is because if you actually wanted to show this rigorously, we would need to use something called induction. And induction is not something that I'm going to teach you. It's something that even when we teach it to the first year proofs students, they don't tend to like it. So, I'm not going to ask you to do it. So generally, and you can see the writing assignment was a little bit of this as well. I am very much okay with you saying, we've computed a couple derivatives. We've recognized that this is the pattern. And so we believe that this is the answer and that in my mind will be sufficient reasoning. Okay. It's just, it'll come down to pattern recognition here. All right. Any questions about that? That's not too bad. We'll do a couple more examples. That's really what the emphasis of today's lecture is going to be, is these pattern recognition for higher order derivative sorts of things. Okay. And some of them actually are kind of interesting that they work out. Let's try. Not that one, but let's try. Where's my mouse? There it is. All right, so let's try this one. so far so good. Voting seems to be going pretty well.
Kind of wish we had questions like this when I took the course. They're actually kind of interesting.
I feel like we did. Could be misremembering though.
I mean, if we did, they were definitely of a bit more simple variety because we didn't do the combinatoric stuff, so most of the students wouldn't really recognize factorials and whatnot, right?
Sure. Okay, so we are at about 2/3 voting. So let's do about 40 seconds or so, and we'll take this up. Okay, so about 5-10 seconds, get your last set of votes in. All right, a couple last minute stragglers. And there we go. Okay, so we're pretty, there's a couple of people in the A and B categories, but C and D are pretty split, I think pretty evenly. Let's very quickly breakout rooms this and see if we can come back with a good answer. I've got a really nice one, but did we put it on the test? No, we put it next week.
What do you mean by nice?
There's a great question we're going to do next week, which involves the, oh, you know what? It will kind of come up this week. But it involves what's called the Hermite Polynomials, right? So you can wiki those if you like. Now, the Hermite Polynomials are defined entirely in terms of derivatives, but you can't write them down explicitly because there's no closed form for the nth order derivative that you need to be able to compute. Now, they appear all over the place. The Hermite polynomials are some of the most important polynomials you can get. In fact, it's crazy that they turn out to be polynomials given that there are exponentials in their derivative. Yes, exactly, Batuhan, spelled like that. And so they show up all the time, all over the place. They show up in quadrature. They show up in, partial differential equations. They show up in quantum physics. They show up in lots of different places. But are relatively, you can define them in a first-year class just once you have differentiation. Problem is, though, actually, we need the chain rule. So that's why they are not in this week. They're actually next week. This week, we will do a different set of polynomials. Those are just the people who don't want to go. There's almost always, yeah, and I've thrown you into one if you want to go, but I think we're going to call people back pretty quick here, Haysam, so it might not be worth it. You might just want to hang out. Yeah, no, there's usually about 10 to 15 people who just really refuse to do breakout rooms on principle. That's okay. Yes. By they, do you mean we, Sarah? I believe you are one of the people who have a very strong opinion about breakout rooms. Exactly. Oh, damn it. Sorry, guys. I ended the polling when I meant to close the rooms. So those who voted, you're going to have to vote again. Sorry about that. But I'm sure you all enjoy clicking buttons, so it's probably not that big a deal. I hope. You all had the right answer anyway. All right. So we're coming back, and yeah, we're overwhelmingly heading towards the right answer, which is pretty cool. I like to see that.
So close, Tyler.
Oh, that's okay. It is what it is.
It'll happen one of these days.
Yeah, we'll get there. Okay, we're at 82%. I'm going to give you about 15 more seconds to get those last couple of votes in. All right, we were close. So we had 92% on D and 8% on C. In this case, the mob is correct. So the answer is D. And, you know, I really, I think there's something kind of nice here, which is if you don't do enough examples, like if you only do one or two, I think, derivatives, you might actually mislead yourself. And that does sometimes happen. There are a couple of instances in which we can create examples where you might get the wrong answer because you just didn't do enough examples to correctly see the pattern. Okay, so you always want to be careful of that. Just make sure you do enough examples that you can be really confident about what the pattern is. All right, so the question was, we had f of x was e to the 2x, okay? Now we've seen a problem like this before. If you know the chain rule, how much is usually enough? I would say by the third derivative, you've got a pretty good idea. By the fourth derivative, you should be 100% correct, right? You can often get it a little bit earlier, and depending on how much you practice, you might be able to snipe it really, really quickly. Like you'll be able to see potentially factorial show up and stuff like that. 4 derivatives, you should never have to go more than 4 though, right? But yeah, it's like Jordan says, it's definitely probably better to be safe than sorry, right? Now, for those of you who know the chain rule already, you can, of course, just eyeball this and you know what the derivative is. But because we haven't technically done the chain rule, I'm going to differentiate this by writing this as e to the x times e to the x, right? That's, remember, when you have the same base, you would add the exponents. So this is one way that we can write this so that we can apply the product rule. And like I said, this will become much easier once we've learned the chain rule. But for now, right, we're going to differentiate the first times the second plus the derivative of the second times the first. And the derivative, oh man, I keep tongue twisting that one. The derivative in both cases is just e to the x, right? So we're just going to get e to the x times e to the x plus e to the x times e to the x. And that's e to the 2x, right? Kind of reusing this fact. Plus e to the 2x, that's 2e to the 2x. All right, now we're going to reuse this fact, okay? Kind of let's maybe put this in a box somewhere because that's really useful. 2e to the 2x. Okay, so that's our first derivative. Now, we probably only need maybe 2 or 3 here. Okay, so we're going to compute the second derivative, which means I'm going to differentiate this, and I'm just going to write it like this so you can see what I'm doing. And I'm going to pull that 2 out. Okay, and now we don't have to go through all of that work again because we already know what the derivative of e to the 2x is, right? It's in that yellow box. Right, exactly, Jude. You can't use the power rule here. So the power rule only works when the x is in the base. And so it's like x cubed or x to the 4, x to the 5 or something. When you have an exponent and something like 2 to the x or 3 to the x or e to the x, you can't use the power rule and you have to use logarithmic differentiation. Yeah, exactly. Okay, and now we know what this derivative is, right? It's in the yellow box. So we're just going to write that down, right? So we're going to get 2 times 2e to the 2x. And again, anytime you're doing these problems, don't actually do that multiplication, okay? Don't do 2 times 2 and write it as 4. I would just leave it as like 2 times 2 e to the 2x, okay? Because when you're looking for things like factorials or when you're looking for things like powers, it'll be easier if you haven't done the multiplication in and done that simplification, okay? To just make your life a little bit easier. Now, the problem here, if you stop here, so this kind of eliminates the factorial option, right? Because we don't have 3 times 2 times 1. We have 2 times 2. But at this point, I don't know. Is it going to be like, am I going to get 2 times 2 times 2? Or is it just like, is it going to give me 2 times 3, right? Like, am I just doubling the number each time? Or, am I going to get a power? So let's do one more just to be on the safe side. Really make sure that we're comfortable with what the answer is, right? So I'm going to take out that 2 times 2. And then differentiate the e to the 2x one more time. Oh, okay, now we can see kind of what the pattern is, right? It's 2 times 2 times 2 e to the 2x. All right, so if we want, we could write that as 2 cubed e to the 2x. So when we look at these, we see, okay, well, how many 2's show up? Oh, the same as the number of derivative. And then everything has that e to the 2x, right? That e to the 2x just shows up absolutely everywhere. So that suggests to us that our answer is just going to be 2 to the k e to the 2x. Okay, and that was answer D. The D used, n instead of k, but of course it doesn't matter. Okay, so hopefully that makes sense. And again, you just want to do enough just to make sure you can really, you're confident that you're seeing the pattern. And hopefully you do see this, right? Every single time I differentiate, all the 2's that I've collected so far are just going to hang out, and I'm just going to get another one showing up from when I differentiate that e to the 2x, right? It's just a 2 factory. Every time I differentiate it, another 2 pops out, right? So it's just a little 2 factory like that. Okay, so any questions about that? Is this unit covered in the test? Yes. Yes, it would be. This is the higher order derivatives part. So the very last thing in the test information is that higher order derivatives show up. Yeah. All right. Let's go. All right. Now this one you can probably guess might be a little bit trickier. It's not too bad. Okay, I don't want you to freak out. I don't want you to worry. But what is this one? Oh, let me relaunch the poll. Okay, so we're at about 2/3 now. So let's do 40 seconds and finish it up, get the last of the votes in. How do you know? Ah, yes, I see. All right. So here we go. We're leaning towards C. I'll say that for a long time, A and C were definitely tied. B and C are pretty close. I think they're just one off of each other. Like 7 people voted for B, and 8 people voted for D. Let's do some breakout rooms. Again, we'll try and keep it a little quick here. See how it goes. We can try another example later. What life has taught me, huh? I don't know. I probably have some interesting, profound lessons in life, but can't think of them. Yeah. Yeah, I think there's what school has taught me. I mean, there's all sorts of things, right? Lots of little things, lots of things like one of my favorite lessons in life is that you can do what you want, and that you shouldn't be afraid to ignore the advice of society and ignore the advice of whatever your culture is. Okay, a lot of people do things because it's what everyone else does, and a lot of people do things because that's what society tells them that they're supposed to do, and that's nonsense. That's BS. You know, people don't want to think, and people are afraid to think, because if you think, it means that you have to make your own decisions, and if you have to make your own decisions, there's a chance that you could be wrong. And people will tell you, go to school and then get married and have a house and pump out a kid or something like this. Every society is different, every culture is different, but most societies have this sort of rough timeline of what you're supposed to do and when. But the reality is most people don't think about, is that actually going to make me happy? Again, because they don't want to think about it. And so instead, at some point in your life, you should sit down and just be like, is this actually what I do? What I want to do? What do I want to achieve? What are my dreams? What will make me happy? And then to do that instead, and to not worry about what society thinks, and to not care about whether you're counterculture or you're doing something that other people don't agree with. It doesn't matter, right? Think about what's going to make you happy, not what society thinks should make you happy, because that's stupid. And once you realize that you don't have to do what everyone expects you to do, your life becomes very liberating. And I think that you'll be much happier kind of overall for it. How do you find a 9 to 5 job that you thoroughly enjoy? I don't know, Thalen. I don't know. I mean, I think, I have been very lucky. I do something that I love because I both love mathematics and I love teaching. And it's certainly not a 9 to 5. I mean, hell, it's, locally for me, it's almost 6 p.m. So yeah, I don't know. I can't comment on that because I honestly don't know the key to that. Yeah, definitely. Sometimes it goes late. But something else that I've learned is so much is about perspective, right? I remember the first time I ever learned this, I was sitting in grade 9 French class, right? And I just hated that class and I didn't have to take it. So I started doing quite poorly in that class as a result. And I realized that instead of thinking about how much I hated that class, and instead of thinking about how much I didn't want to do it, instead I kind of changed my perspective. And I said, okay, well, what I'm going to do then is instead of thinking about all those negative things, I'm going to think about this as a challenge instead. I'm going to challenge myself to do well. Or, just these like subtle little perspective shifts or paradigm changes. And then once it became a game to me to see how well I could do, it wasn't, I started to enjoy the game. I still hated the French, but I enjoyed the game. And that love to enjoy what you hate to do what you, yeah, right. You know what I mean? Like if you can make games out of things or find ways to take pleasure in things. Because listen, one of the rules, one of the surefire things of life is you're going to have to do things you don't like sometimes, right? You just can't avoid that. But if you can find the pleasure in things and you can find the joy in things, even if it's just because you challenged yourself and you enjoy rising to that challenge and seeing your gains and seeing yourself accomplished, then you'd be surprised at how easy these things become and right, like find a way to enjoy things. So that for me was very a lesson I luckily learned very young, right? And have used that many times in my life when I find something that I really don't enjoy doing and say, try and find the good in it and focus on the good and and then you'll enjoy it and then it's not a problem. So yeah. Okay, so let's do 20 more seconds here and I'll wrap it up. There's lots of these little things. That's true, that it is recorded, so everyone can get this in posterity. Okay, so let's take a look at this. Beautiful. We've got C here. I'm pretty sure C is the correct answer. So let's take it up and let's see how that goes. Like I said, there's always, off by one potential issues. So I think the first time I did this, I was actually off by one somewhere. And because I made this question and then when we went over it as an instructor team, they were like, oh yeah, you're off by one. So let's, I want you to double check my work too and make sure that I've done everything correctly, okay? So f of x, here our function is 1 over x, all right? So let's just start differentiating. So the first derivative, or maybe let's write that as x to the power of -1, okay? And I'm going to keep it like that pretty much the entire time, just because it's obviously easier to differentiate it like that, because then we can use the power rule, right? So f prime of x, again, I'm going to pull down the -1 in front, and then I'm going to subtract 1 from the exponent, right? So I'm going to get -2 like that, okay? So let's differentiate again. Second derivative. Now I'm going to pull down the -2, and I will have x to the -3. And like I said, let's do 3 derivatives because this is going pretty quick. So -1, -2, -3, x to the -4, and we'll do one more just because it doesn't hurt. So we get -1, -2. And again, you can see I'm not doing the simplification, right? I'm deliberately kind of leaving them like this, okay? So now at this point, we're looking for patterns. So one thing you want, and actually, you know what, it might not hurt. Maybe let me write out what these actually are. So this is -1 over x squared. This is 2 over x cubed. This is -6 over x to the 4. And this is, what, 24 over x to the 5? Okay, so sometimes if you do it kind of both ways, you can help see things. So one thing I want to point out here is notice that the signs are flipping, right? When I take the first derivative, I get this negative thing. When I take the second derivative, I get a positive one. When I take the third derivative, I get a negative thing. And when I take the fourth derivative, I get a positive. And the reason for that is because you can think about me, if I were trying to factor the negative signs out of each of these numbers, I'm trying to count how many negative signs appeared, right? So when I take the fourth derivative, I got 4 minus signs, right? Does that kind of make sense? And then what's left over? So 1 times 2 times 3 times 4. Okay, well, I took 4 derivatives, and that number to me looks like 4 factorial, right? So maybe just kind of let me make these simplifications one step at a time. Okay, and now when I took 4 derivatives, okay, well, I didn't get a 4 in the exponent here, right? That's not a 4, that's a negative 5. So that seems like it's going to be 1 less than the number of derivatives I take. Or if I write this as negative 1 to the 4 factorial divided by 1 over x to the 5, I'm going to have, it seems like the exponent is 1 higher than the number of derivatives that I took, right? So my hypothesis then, right, the thing that I suspect should be true, is that I'm going to have negative 1, or I guess I've been using n. Let me change this to n. So I'm going to have negative 1 to the power of n, right? Because I got these n negative numbers, and I was able to factor a negative 1 out of all of them, times n factorial divided by x, and then 1 more than the number of derivatives that I took, right? And that answer is that C? Yes, that is C, right? That is exactly the C answer. Okay. Now, the other thing you can do as well is if you don't see that you should have pulled the -1 sign out of each of them, you can just say, okay, look, I know it alternates signs, so it has to be either -1 to the n or -1 to the n plus 1, okay? Because that thing, that -1 to the n or -1 to the n plus 1 is how you make things alternate signs. And so now I just need to make sure that it lines up. So when I take 1 derivative, so when n equals 1, I need to have a negative answer. And if I plug n equals 1 into both of these, this is the one that's negative, and this thing here is positive, right? So it says I don't want that one, and so it should be -1 to the n. So that's another thing that you can do there, which is you can just pattern match that way, okay? So hopefully that makes sense. Is everyone okay with that, I think? And of course, it's not the only way you can do it. You can try to match those patterns in a slightly different way. So you didn't have to do it exactly like I did, but hopefully it seems like most of you got to the right answer, right? Okay, now let me ask you guys what you want to do. So I have another higher order derivative question, and then I have a higher order derivative question, but it's slightly different. So, okay, sure. Well, some people, actually, you know what? I guess nobody has to leave at 6, right? Because we definitely are still in lecture time. So maybe let's just kind of stay the course for now and see where we're going. But of course, if people need to leave, of course, we will publish the slides, so you will be able to see what the other question was anyway. Okay, so here's another one. You have x e to the x. Okay, this one I think is going to start off nasty, but once you've done 2 or 3 derivatives, you're going to be like, oh yeah, I see the pattern right away. I hope at least. Okay, so we are at 2/3. Let's do 40 seconds or so to wrap that up. All right, A has a pretty commanding lead. It's more than twice as much as anything else. I'm not certain that, right? Like B has 5 votes, C and D are both tied with 10, and A has 21. And the majority of those votes actually kind of came in at the end. So I'm not certain that breakout rooms are going to be useful for this one. So let's just take up the answer. A is the correct answer. So good job for those of you who chose A. And let's see why it's A. All right, so our function f of x equals x e to the x, right? Okay, so we're going to have to product rule. So let me, again, just kind of break it into steps. Again, for those of you who have lots of practice with the product rule, of course, you don't have to do this, but let me do it so that people can kind of see what's going on. The derivative of x is, of course, just, oh, wait, why is my screen not showing up? Did I drop? Damn. Yes.